Hello, welcome back. Now we move to lecture 8, and we are going to devote lecture 8 to an approximation for the exchange correlation functional that we introduced in last lecture. And that approximation is the first one that was made even historically, is the local density approximation. We are going to spend time to describe it. It's pretty simple, in fact, and then we are going to show that it's pretty successful at predicting properties and also explain why, in spite of its simplicity, it's actually pretty good. So let's try to summarize a little bit what we've done last time in the last lecture that was devoted to the Kohn-Sham theory. So if you remember, if you take a step back, Hornberg-Kohn theorems established that there exists an energy functional of the density that we can minimize for all densities, and then with the density that minimizes that energy functional will be the ground state energy, will be the ground state of the system. Now, this is a nice way to put it. The problem is that Hornberg-Kohn does not give you a prescription to build the energy functional. And so the second piece of the puzzle came with the Kohn-Sham theory, which essentially established a method to be able to build that energy functional. And not only just a method, but also a practical way to make it happen. So the way it's done is that in Kohn-Sham theory, um, auxiliary problem is defined, and that auxiliary problem corresponds to independent particles. I should say that that system is not a physical system. However, it is built in such a way that we can create the density of the density that corresponds to the solution of that independent problem is exactly the same by construction to the density that we are looking at. So that's what makes it so nice. So the independent particle equation from Kohn-Sham is the first equation in this yellow box here. And of course, the price to pay is that we have to come up with effective external potential, which I highlighted in the blue box, which is not just the external potential of the real problem, but also a piece that's related to the Hartree potential, as well as what's known as the exchange correlation potential. Now, why is it so useful? Well, it is useful because it turns out that the exchange correlation potential is just the piece we don't know, that we can't calculate. So if you look at in the box at the bottom, what we know is the kinetic energy of the independent particle, the energy to the external potential, and the Hartree potential. So it turns out that that piece that's known is the largest chunk of the energy. And so what we don't know is then the exchange correlation potential, exchange correlation energy. So uh, sure, numerically, the exchange correlation energy is small compared to the rest, but of course, the exchange correlation energy also includes everything that's quite interesting from a quantum mechanical standpoint. So numerically, it is small, but of course, in terms of physics, it's important. But the good news is that thanks to this prescription now, we can try to find a way to build different approximations for the exchange correlation potential or the exchange correlation energy in order to actually make all this work. So I'd just like to remind you that the Kohn-Sham equations are exact. There is no approximation in there. This is just that there is a term we don't know, which is Vxc. They correspond to single particle equation. So the equation here in the first equation, the yellow box, is actually much simpler to solve than the full problem because the wave function or the orbital, the Kohn-Sham orbital psi j, are just orbitals of a single electron, much simpler to solve than an electron. And then, of course, we have to approximate the exchange correlation energy. So I like to put this in contrast with what we did for the Thomas Fermi Hartree theory that we did in lecture 6. In that case, we were approximating the full kinetic energy functional, actually with the homogeneous electron gas. And so that was just too bad an approximation. I mean, just too far away. But here, the big chunk of the kinetic energy is approximated by that of independent electrons, which is the largest piece. And for that, I like to show you an example here for the helium atom. And I like you to focus on the table at the bottom. And the table at the bottom is, and I'll just focus on helium in there. If you want to look at the others, I invite you to pause the screencast and look at it. But what this is saying is that the correction to the kinetic energy, for example, for helium, is just a tiny fraction, is about 1%. So the TC there, the TC is about 1% of TS. So we get most of the kinetic energy correctly using LDA, using DFT, Cohen sham. The electron-electron interaction, so VEE, is very well approximated by the Hartree part, U, minus the exchange part. So if we do that, we see that the correction to the electron-electron interaction, UC, is actually also pretty small. As a result, the EC, which is the full correction that we need to do from the correlation piece, is actually pretty small compared to the total energy. So that's what's happening. So that really shows that the piece we don't know is actually pretty small. I should say here at the outset that the exchange energy is actually not a small number in general. So the exchange energy is an important piece, which is also why the Hartree-Fock theory was not too bad, because the exchange energy is exact. By using a Slater determinant, we make sure that the solution is antisymmetric, which is exactly the exchange energy. So I should say that. And what's also interesting is that we see that all those terms keeps being small compared to the total energy that we are talking about. So this is actually why a posteriori this approach of using what's known, so basically the middle column in this table is the biggest chunk compared to what's unknown. So people have come up, as I said, the problem that came up that's only there that's left to solve is to find an approximation for the exchange correlation potential. And people have come up with a number of approximations, which we will explore in the rest of this course. But the first one is the local density approximation. Now, remember, we are working with functional of the density, and you should already remember from our introduction to functionals that a local density, local functional, is basically a functional that only depends on the density itself at a given point, and not for the derivative. It's exactly what we are going to see. So LDA is the simplest approximation to the exchange correlation, and it's actually built in a pretty much similarly to the Thomas Fermi-Hartree approach. You remember for Thomas Fermi-Hartree, we were using the kinetic energy of a homogeneous electron gas, a non-interacting homogeneous electron gas, and we were also using the exchange of the homogeneous electron gas. So we were using that. Now, what we do now is do the same, but the big difference with the Thomas Fermi-Hartree approach is that we do not approximate the whole kinetic energy with the homogeneous electron gas. We only approximate the exchange piece and the correlation piece. So that's a very different story, because the rest, the known part, is the one from the independent electrons. So we can calculate the exchange energy exactly in terms of the mean density. I already discussed this in the lecture on the Thomas Fermi. I also provided the result without proof, and I do this again here. And then we find what the energy of the homogeneous electron gas for the exchange is. It depends on 1/3 power of the density. Similarly, we can calculate the correlation piece for homogeneous electron gas. And this one is not exact. We cannot really calculate it analytically, but it can be calculated numerically. And there have been different methods to do that historically. One of them being the quantum Monte Carlo approach, the very well-known approach from Sepperly-Adler, using quantum Monte Carlo, allowing to get essentially the exact correlation for homogeneous electron gas. So there are different ways to parameterize the finding of Sepperly-Adler, and all these are used currently in the description of LDA. So this is a term that looks like this. I am not providing you the exact form of the lowercase ec, but this is what's calculated by the methods like quantum Monte Carlo, for example. So that's so there are different approaches for the correlation piece, and usually there are not that big differences between them. So one thing we can say is that in LDA, that's it. By the way, that's a different description of the LDA exchange correlation. The piece that we are missing, so the exchange and correlation, is provided by the exchange and correlation of a homogeneous electron gas, which is essentially exact for practical purposes. It's not analytical, but it's exact. And I'd like to show you the next result to give you an idea of the exchange and correlation. So this plot here is the x-axis is RS, which is the Wigner-Seitz radius. Basically, the Wigner-Seitz radius is the average size of a sphere that contains one electron in the system. So that's basically the difference between a dilute system versus a high density system in LDA, for example. So this is the result for the uniform gas. And then you see that both the exchange and correlation got closer to zero as we get a more and more dilute system, as we would expect. But what's more important in this plot is the fact that the exchange piece is always larger in absolute value compared to the correlation. That's just a fact that the exchange is larger than the correlation. We'll discuss this much more. Now, we could say at the outset that this approximation of the homogeneous electron gas shouldn't be too good. Because, well, most systems, if you think about molecule or even surfaces or adsorbates or what have you, they are very far from a homogeneous electron gas. You could say that, and that would be a good assumption. However, as we shall see in just a few minutes, this approximation is actually pretty good. But let me see why it would be surprising if it were good. Essentially, what matters is the top equation on this slide. This top equation tells you that the exchange correlation in LDA is a local approximation, which means that the functional is just a functional that depends on the density itself and not on its derivative or change to it. Now, what it means in practice, if you look at the plot at the bottom, is that the contribution to the energy only depends on the density. So if you look at the green plot there of the density on the left, you see that even though 2 points that are highlighted with the purple dots are very different places in the density. I mean, they correspond to a minima or to going downhill for the second one. But yet those 2 points in the density contribute exactly the same in the exchange correlation. Clearly, we do not expect this to be true, but at least we have a place to start, right? Now, one thing I'd like to tell you, in the last lecture, we discussed about the energy that we calculate using the Cohen-Sham orbital and the Cohen-Sham eigenstate, eigenenergy epsilon j. And you may have wondered back then why the two terms in that box do not cancel, the last two terms, the exchange correlation and the exchange correlation energy and the integral of the potential. Well, I can actually show you this for LDA now in the simplest case. Of course, we know that the exchange correlation energy in LDA is given by this local expression. We can calculate the potential as being the functional derivative of that energy. And when we do that, and this is where learning about functional derivative was useful, we find this result here. Of course, the derivative of the product is just the sum of the derivative. And so we obtain that, which is nice because now we see that if we evaluate what we have in the blue box using the information that I just obtained, we see that there is a term that's left, which is related to the density times the derivative of epsilon with respect to the density. So That's very nice. And the expression, of course, in blue is not zero. So the two terms do not cancel. That gives you a hint. Now, LDA, historically, um, you would not expect it to be too good, but it turns out, and this was quite surprising actually, in spite of just including the corrections related to homogeneous electron gas, LDA, in fact, was very successful. Um, it's extremely simple, but it works very well. And even in systems that are very far from being homogeneous or quasi-homogeneous. So this approximation works pretty well, and in fact even reproduce bonding and reproduce a lot of experimental data pretty close in terms of bond lengths, mechanical properties, and so on. Not perfect, but pretty good. And as we shall see by the end of this lecture today, there is a reason, a fundamental reason why the LDA is actually pretty good, and it's because fundamentally the theory fulfills a number of sum rules, especially the one on the exchange correlation hole, which I will describe, which I will describe in a few minutes. Now, the main thing about LDA, and this is actually the main thing to remember, is that yes, sure, LDA is good, but it's mostly due to cancellation of errors. So we end up having a lot of properties that are not necessarily expected to be good with LDA, but because of a lot of cancellation of errors, it's actually working well. So, for example, the exchange in correlation, which is what we are trying to get right, it turns out that LDA pretty grossly overestimate the exchange, but at the same time, it underestimates the correlation. As a result, the sum of the two is actually pretty accurate because the overestimation and underestimation are of the same order of magnitude, the same amplitude. Um, this is not luck, as we are going to describe. This is not luck. I mean, it's because the sum rule on the exchange correlation hole is being fulfilled. Now, one other thing, as a good thing to remember, is that LDA is actually pretty good when the electron density tends to very high value. So when you have a high density, you have a pretty good approximation with LDA, and this is also why it corresponds it reproduces bonds very well. And the reason for that is that when you have a high density, you have a very large kinetic energy for the TS, and as a result, uh, what is known, so like TS, is actually much larger than what is unknown, the exchange correlation. So even if the exchange correlation is not very good, the kinetic energy being so much bigger, then of course we have a good description in that case. So for the very high value of the density. So that's what gives us why also LDA is good, because of course what is of interest when you look at a solid or a molecule is the bonding, and the bonding correspond to those areas of high density. Now, LDA is not necessarily your exchange correlation of choice in spite of its success because it has drawbacks. Some of the drawbacks is that LDA tends to overbind actually. What we mean by overbind is that it gives a too high formation energy, and actually even more obvious is that when you calculate bonds, the bonds is usually shorter. The bonds are usually shorter in LDA. You can spot an LDA calculation pretty easily by looking at the bond lengths are usually much, I mean, not much, but certainly significantly smaller than they would be experimentally. And LDA also has an issue with not localizing electrons enough in space. So LDA tends to have a dilute system. And so this is something that's important, in fact, when you do calculation in reality, because those orbitals that we talk about, so the atomic orbitals that are involved, for example, sp, d, and f, like in this plot, uh, each of them show a different level of localization. And for instance, the D and F can be very localized close to the ion. For D and F orbitals, LDA is usually pretty poor. But for S and P electrons, LDA is pretty good because the electrons are not as localized. Another thing that's important, and we will spend a full lecture on this maybe in a couple of weeks, in a couple of lectures, The long range effects, like image effect, like when a charge is above a metallic surface, it interacts with the surface as if there was an image charge in a mirror, mirrored inside the metal. That one is a non-local effect, and it's definitely not included in LDA. Van der Waals bonds, which are actually very important, especially these days where we look a lot at layered materials, where the layers are interacting um, through Van der Waals interaction. Those long-range effects are completely missing. Now, I have to warn you about Van der Waals interaction. If you do a lot of calculation of benchmarking of Van der Waals system, like for example, 2 layers of graphene in LDA, you will find that LDA predict the right answer. And this is something that I personally fight, not fight students, but I fight to make sure that students are aware of this. Sure, LDA seemingly give you a pretty good answer. It does. I mean, LDA for graphene, for example, of bilayer graphene is going to give you the right bond length, the layer distance to about 3.4 angstrom. But in spite of this, LDA does not reproduce van der Waals well. So it sounds a little bit contradictory. It's not. It's the reason why LDA is able to reproduce this 3.4 angstrom is actually a cancellation of error. So it's not true that LDA represents van der Waals interaction well. It's just the symptom. The LDA suffers from illness, but the symptom do not show the illness in that particular case. Hydrogen bond, same thing. It is not very good in LDA. But when you look at the density, and if you compare for this example, this experimental data for zinc selenide on the left, and you compare between Hartree-Fock and DFT, you can see that the overall, qualitatively, of course, we cannot do much more than qualitative. DFT, and it's LDA in this case, is doing pretty well. And Hartree-Fock was not doing too poorly either. But the point is, DFT, in spite of its simplicity for the LDA, is doing pretty well. And I have to tell you that for large system, Hartree-Fock can be very expensive. So actually, Hartree-Fock is not necessarily a very cheap method numerically, but LDA is actually give you something similar in spite of its simplicity. So I can tell you more about LDA and it's important. And before we do that, maybe it's a good idea to repeat what we've done so far. So we have solved those equations. I'm not going to repeat the equation in the yellow box anymore. The goal of LDA is to find an approximation for VXC or EXC. And as I told you, in the case of the exchange part, we borrow the exact exchange energy for the homogeneous electron gas, which of course only depends on a constant, which is the density if it's homogeneous. And we expand this, since this is the blue arrow on this slide, we expand this to a density that varies in space. This is a big leap, but that's what exchange is done in LDA. For the correlation piece, we do something similar, but in that case, we use actually the correlation that's obtained from quantum Monte Carlo, for instance, from perturbation theory. Okay, so we know that when we look at system like solids or molecule or what have you, the system is interacting and is not homogeneous. And so we are able to, in spite of that, we are able to use LDA to explain those things. Remember that the fact that we are using a homogeneous approximation for the exchange correlation, we are still treating the rest, the independent piece, exactly, if you will. I mean, we have a good description for it. At least the operators are exact. And so the interaction is also included. So we solve the problem we solve everything by using it's because we are separating this in two parts. Sorry. One is the non-interacting particles. This is the Kohn-Sham equation. And then we add the exchange correlation energy to that, to the mix, which in this case for LDA. So we do all this and we connect the whole thing through the effective potential. So in particular, the local density potential, exchange correlation potential, which we do by connecting the full problem to the problem of the Kohn-Sham equations. So what I just said, I just used different words to say the same thing I've said before. This is nothing new here. Okay, so as I said, why is LDA so good? I mean, it's kind of surprising that LDA would be so good. And it works great because of a systematic error cancellation. As I said, LDA underestimates the correlation, but it overestimates the exchange. As a result, is that the sum of the two turns out to be pretty good. I would say, and I've said this before and I'll say it again, this cancellation of error is not accidental. It is actually systematic. It's one of those cases where we are lucky, but it's actually not luck. It turns out that there is a fundamental reason why it's actually not bad. And then we are going to explore this before the end of this screencast today. So LDA has been used a lot by solid-state physicists for more than 20 years, maybe 25, 30 years. At the beginning, quantum chemists were not that convinced. In fact, quantum chemists don't usually use LDA. I mean, if you talk to a quantum chemist, I'm talking from my own experience over the years, because I've worked with quantum chemists in my life quite a bit. And if you talk about LDA, they're either going to raise their eyebrows or they are going to smile. So, and it's not because they find it funny, it's because they say, which quantum chemist is going to use LDA? But don't worry about it because improvement on LDA will come up in the next lecture. But the reason why the quantum chemists do not use LDA is because Hartree-Fock is actually at least as good for molecules. So, when something works, having people change their habit is actually very difficult to do. I mean, why would you change something if what you have worked just as well? So for LDA, it was not terrible, but not an improvement compared to Hartree-Fock for molecule. Now, for solid and for surface and in solid state physics in general, DFT is superior to Hartree-Fock. So that was already solved from that perspective. One other thing I'd like to mention is that I didn't talk much about spin, aside from the fact I spoke a bit about exchange at some point. But all this LDA and DFT in general, we can use a spin polarized density. So we calculate the density for each spin up and spin down. We can do that. It's actually part of every single code that we are using now. There is no particular difficulty. Now, the advantage of this is that we can now look at the effect of having a material in a magnetic field. We can calculate antiferromagnetic state or ferromagnetic state. So we end up having the possibility of looking at the magnetic response. Now, I should also say as an aside is that LDA might not be the best choice because many systems that show interesting magnetic properties are like a system with F electrons. And then I said F electrons are highly localized, and highly localized electrons, LDA doesn't do too well with that. Okay. So I just want to make sure that we keep track of what we are doing. We have a very simple approximation for the correlation. But remember, correlation is actually very complex. We do not have the recipe to calculate correlation for everything. We just don't know how to do it. So it's complex. We are doing approximation. This approximation is pretty crude, but it seems to be working for a vast array of different materials with exactly the same exchange correlation. So that's another thing I did not insist too much on so far, but the fact is these functionals are not system dependent. Sure, they sometimes work better for some system than others, as I mentioned, but you have one LDA. It's not like, oh, I have one LDA for carbon, I have one LDA for nitrogen, and so no, you have one LDA description, which is, of course, makes DFT so attractive. Okay, As we said, the exchange correlation piece is much smaller than the rest, which is a good news. And then we hope to be able to understand how everything works. Now, before I stop this screencast, I'm going to spend the next, I don't know, maybe 10 minutes or so to tell you about why things work. And for that, I'm going to tell you about the exchange correlation hole. This is something I mentioned to you before, uh, even in the Hartree, in the correlation hole in the Hartree-Fock theory, but this is such an important concept and actually pretty easy to understand that I am going to use it. And for the first time, I'm actually going to formalize it with some math. And this is actually the math that are going to explain to us why LDA works so well. So of course we have electrons. Electrons tend to avoid each other. So if you use a mean field approach, you are not taking into account the existence of an electron somewhere for the position of another electron. So I already discussed that in much detail. I am going to discuss it much more now, but maybe not using the same words, hopefully. So the idea is it's similar to having an electron that if you have an electron somewhere, the probability of finding another electron close by is reduced just because the electron repulsed. So it's a little bit as if the electrons was creating a hole around it. And the hole has two origin. It has exchange and correlation origin. So it does not, it's like a no-fly zone as well, if you will. It's basically saying, hey, I'm here. You probably don't want to get too close to me or you're going to get burned. That's basically the idea. So that effect is a pure correlation effect. And this is what is actually difficult to get. However, uh, it leads to interesting theorems that we are going to work out now. Now, if you look at the equation at the bottom of the slide here, it's reminiscent to what I described in a lecture on Hartree-Fock when I was talking about that what we should really need there is a conditional probability. And so the conditional probability PRR prime is really the probability of finding a pair of electrons at R and R prime. So it's a probability of finding electrons at R prime, and then we divide by the distance between them, and then we integrate, and we do get the full electron-electron interaction. This is not an approximation. I like to insist on this. This equation here, if I knew P, which of course I don't, but if I knew P, which is the pair distribution, exact pair distribution, including correlation, this equation would be exact. Now, in Hartree-Fock, we approximate P by the product of the density of n of R and R prime. So in other words, we do not include the correlation between them. But so let's have a look a little bit more about this pair density. So the pair density can be obtained by integrating, if we knew the full body wave function, by integrating the full body wave function. And we have n minus 1 in front to make sure we have a normalized pair density. So a normalized number of pairs, right? Of course, which is of course n times n minus 1. So this is the number of possible pair that I have for n electrons. Now, this is the way to calculate it. Now, the next slide is the important slide, and I'm going to spend a couple of minutes on it, just to look at this pair density. Now, the first equation on the top of this slide is telling you that what is the probability of having an electron at x and x prime. So in a pair of electrons, one at x and one at x prime. And we multiply by the volume d cube r and d cube r prime just to make sure that it's the number of electrons rather than a density, okay? Well, of course, it's that pair distribution is the density, the number of electrons at x, times the number of electrons at x prime if there is an electron at x. So the n2 x prime is the conditional probability. So if you're not convinced by this, it's actually related to Bayesian statistics. So pause the screencast and you might just click in 1 minute. The point is n2 x prime is the probability of finding an electron at x prime if there is one at x. And of course, if I multiply this by the probability of finding an electron at x, I do get the probability of finding a pair of electrons at x and x prime, right? This is, I teach this, And each time I prepare my slide, I have to spend a couple of minutes to remind me, even though I work in DFT. So you are totally forgiven if you have to pause the screencast and take a minute to understand this, right? But it's important. Now, it is clear from the definition of the previous slide of the pair distribution function P that the integral of that pair function over all the electrons is going to give me the density of x times n minus 1. So you can look at that mathematically from the previous slide, or, and I'm talking about the first integral on this slide here, at the bottom of the slide, or you can just think, if I consider every single pairs x prime, if I integrate over all the space, right, all the space x prime, of course, what I get is the density of one electron being at x times n minus 1, which is all the other electrons, right? So that's clear. If you're not convinced by that, by the English version of it, you can look at the math. Now, as a result, if I apply that integral to the equation on the top of the slide, we directly know that the integral of n2 prime has to be n minus 1. It has to be n minus 1. And again, you can actually either convince yourself mathematically, or more obviously, you know that n2 is n2 prime is the density of having an electron at x prime if there is one at x. So of course, if you integrate over all the x prime, so you get n minus 1, right? You get the total number of electrons minus the one that's at x. That's basically what it says. So that's actually pretty important. And I really ask you, if you have trouble with this slide, pause it and think about it. The most important result on this slide is the last integral, to convince yourself. And again, n2 x prime is the probability of finding an electron at x prime if there is one at x. That's the most important one. Now, we're almost there. The electron-electron interaction, this is the equation I showed you before. It's an exact equation. Unfortunately, we cannot calculate PRR prime, which is the pair distribution of electron and R prime. But if we could, this would be exact, right? So we can now, what we do, we can write this pair distribution as it's in this box. It's another important equation. If you get it, you're going to get the whole thing. And that pair can be in first approximation. Imagine there was no correlation between the electrons. The electrons do not care about each other. The probability of finding an electron at x and one at x prime, in that case, if there was no correlation, would obviously be the density of an electron at x times the density of an electron at x prime. But we know it's not true. We know that the presence of an electron at x makes the probability of finding an electron at x prime, make it change. So the change that we are using is the correlation, the exchange correlation piece. So instead of having pxx prime equal nx and x prime, as we would be in Hartree-Fock approximation, we correct the nx prime by a correction which called nxc, which is due to the fact there is an electron at x. Right? Now, this piece nxc is essentially the change in the density at x prime because there is an electron at x. This is what I've told you about since the beginning of this course as being the exchange correlation hole. This is the depression, or in fact, it could even be the increase because, of course, you still have to find the electron somewhere, of the density of the electron at x prime if there is an electron at x. And that piece there, that nx prime plus nxc xx prime, is n2 xx prime from the previous slide. Isn't that great? We are almost there. It's beautiful because the equation I told you on the previous slide, if I integrate n2 over all the x prime, we saw on the previous slide that that value was n minus 1, right? At the same time, integrating nx prime over all the x prime is n, right? It's total. Therefore, the integration of nxc xx prime is equal to minus 1 for all x. That's And so it's an integral over dx prime. I'm sorry, I didn't include the dx prime on this slide, but this is an integral over x prime. This is a super duper important result. That result tells you that if you integrate the exchange correlation whole over all space, you find -1. This is one of the sum rule I was telling you. So finding the actual shape of the exchange correlation whole is extremely tough. In fact, it's equivalent to finding the exchange correlation energy. We cannot do it. Well, we can come up with approximation, but this is difficult. This is tough. However, we know a condition on it, and the condition is that that whole has to integrate to -1, right? And this is exactly, and as a result, you can put this all together. The corrections to the exchange correlation now will be given by this equation in the black box, where this is a slightly different from, actually it's very different from Hartree-Fock, because instead of using nr times nr prime, we have nr times the whole, so an interaction with the whole. Okay, so that's nice. So we see that on average, the whole integrate, the exchange correlation whole integrate to -1. So this slide here is basically a summary of what we have. So this is very nice, because when we plot this, when we have this plot here, when we create the whole, we now know that the whole around an electron integrate to -1. That's very important result. And you know, it's not that complicated. It takes about 10 minutes to understand it. Now there is more. There's one more piece. The other piece is the exchange hole. The exchange hole comes from Pauli's principle. In Hartree-Fock description using Slater determinant and so on, we knew how to calculate the pair correlation due to the exchange piece. Okay, this is the what's in the black box here. You can integrate this. You can integrate the exchange hole, and you see that the exchange hole is actually integrate -1 itself. So you can actually calculate that exactly and convince yourself. So on average, the exchange hole around an electron is going to integrate to -1. And you see the exact hole, for example, in this example of hydrogen, which of course should be, we know that should be no exchange. There's only one electron, but we know the exchange actually, we discussed that. Is to counteract the fact that we include the Hartree potential, which should also, the total should be 0. We've done that quite a while back. But don't worry about this. The point is that LDA, you can say, well, it's either a good approximation, the dashed line, or you can say it's a terrible approximation. I mean, I would say it's somewhere in between. But what's nice is that it integrates to -1. So in spite the fact it's not wonderful, at least the sum rule is obeyed and fulfilled. So each electron, one other is excluded. The -1 can be understood by the fact that if we have an electron somewhere, it creates a hole of -1. It basically excludes the other electron. Okay? Now, we can put everything together because we have integrated the exchange correlation hole and find it was -1. But the exchange correlation hole is the exchange hole plus the correlation hole. And what happens in that particular case, right, is that the exchange hole, since the exchange hole has to integrate to -1, the correlation hole has to integrate to 0. So this is exactly what we need for those approximations. Now, this is here what's really great. And this is the most important message explaining why LDA works, in my opinion. Sorry, is the fact that do we have a homogeneous electron gas? No, we don't. But does LDA, this exchange correlation approximation LDA, does it correspond to a real system? Yes, it does. It's actually exact. The LDA is exact for the non-interacting homogeneous electron gas. By being exact, it automatically fulfills the integration rules or the sum rules. So in LDA, the reason why LDA works so well is because the exchange correlation hole integrate to -1, because it is a correct solution for a particular situation. That's also why, even though in LDA the exchange hole is not great, the correlation hole is not great, I mean, for more than one electron, the sum of them, the integral of the sum of them is actually pretty good. And that is why we do have this cancellation of errors. Now, the big problem we have, and this is why the physics of LDA is, I mean, it looks good, but the physics is not always correct, is because we are trading one physical phenomena, which is the exchange piece, which is a Pauli principle, with a correlation piece, the fact that the electron interact with the Coulomb potential. So the two cancel each other, but the problem is you also lose the physics in the game, right? Because if you add more correlation to account for too little exchange, for instance, numerically it looks good, but physically, of course, you have lost something. So the last thing I want to show you is to show you an example for helium, and for helium, we have on the left hand side we have the exchange piece. Actually, this is integrated over. So u is the distance, 2 pi u in front, right? It's actually integrated over a circle. And we have we see that the LDA, we know the exchange in Hartree-Fock is exact, and we see here that LDA is not too bad, but it's a little bit underestimated. So it's really the exchange hole is a little underestimated. But on the other hand, if we look at the correlation piece on the right hand side, LDA is overestimated. Well, it's negative value, so it's more negative than it would be for the exact correlation. So it's overestimated in one case, it's underestimated in the other case, and when you sum them, it turns out that you are pretty close, and the integral, at least, is very good. So just to summarize what we have done here, we I think that we have done greatly. If you have followed so far this course, we have done really well. And in principle, you understand all the operators now. You understand how DFT works. You understand that Cohen-Cham has provided a methodology to solve for Hohenberg-Kohn theorem, so to approach it. And today we came up with a first approximations of the exchange correlation. And what we found, maybe to our surprise, I mean, I was surprised the first time I heard about this, almost 27 or 28 years ago. LDA is pretty good. And we also explain why it is pretty good, is because it fulfills a sum rule on the exchange correlation hole. If you have any question, as always, you can ask in the comments on YouTube. In the meantime, and I'm sorry that this screencast is a little bit longer than usual. In the meantime, I hope you enjoyed this, and take care.